This is a quick overview of section 5.1 in the notes, nth roots and rational exponents. There's one vocabulary term at the start of the section. That would be the nth root of a. Okay, the nth root of a. I think the definition that we originally had in class was a little lengthy and maybe a little confusing, so I'm going to try to shorten it just a little bit. Okay, basically I'm going to shorten it down to this: if b to the n is equal to a, then how does this go? Then b is an nth root of a, not point A. If b to the n equals a, then b is an nth root of a. Basically what that means, and we had this example in class, if 2 to the third is equal to 8, then 2 is a third, or you could say cube, root of 8. Okay, or we could say that 5 to the fourth power is equal to 625. So 5 is a fourth root of 625. Okay, so basically we're looking for that number, multiplying it by itself however many times you need for the root gives you the root. So if I want to know the the fourth root of 625, really what I'm asking myself is what number multiplied by itself 4 times gives me 625, and that's where 5 comes from. Okay, with nth roots, whatever root we're looking for, whether it's square root or cube root or fourth root or fifth root, sixth root, hundredth root, whatever, doesn't matter. We can write it in one of two ways. Okay, let me move this up here a little bit. We can write it in one of two ways. We can either write it with a radical, with an n there and an a there, or we can write it as an exponent, a to the 1 over n power. Okay, now if the number here is not shown, that implies that it is a square root. Okay, so if we have something like the square, that symbol right there means square root. Okay, if we had like a 4 there with an a, that would be the fourth root. Okay, so if there's nothing shown right here, that implies that it's a square root, or the number there would be a 2. Okay, if it's not written, it is implied that it is a 2. Similarly, with the fractional exponents, if we had a to the 1/2, that also means square root. If we had a to the 1/5, that would be a fifth root. Okay, so the number, the denominator of the fraction in the exponent is the root that we are looking for. Okay, we'll get to the point where, or to the topic when this number is not 1 a little later in this video. Okay, so the next thing we talked about in class was real roots. Okay, none of our answers in this section had any i's, no imaginary answers in this section, real nth roots. Okay, the first thing we discussed was how many real roots does a number have? Well, we're still looking at the nth root of a. Okay, and this is where the table comes in that we drew in class. That long table had 3 columns. This was a is less than 0, a is equal to 0, and a is greater than 0. Okay, so that takes care of this part right here. The other part of this little expression in this whole thing right here is this n value. Okay, we need to look at two cases. N is even, and when n is odd, because that makes a difference. All right, let's start with the even side. If the n is an even number, so square root or fourth root, sixth root, 18th root, whatever, as long as that number is even, it fits into this first column. So if we're looking for the square root of -4, that's a 4, -4. we learned in, I believe it was chapter 3, about square roots of negative numbers. That would be plus or minus 2i. Neither of those, since they have the I in them, are real numbers. Okay, the goal of this table is to discuss the real parts of this. So if the n is even, if we're looking for the square root or fourth root or whatever even root of a negative number, you don't have any real roots. So no real roots. If the number underneath the radical symbol is exactly 0. So let's say we're looking for the fourth root of 0. Well, there's only one fourth root of 0. It's 0. Is that a real number? Absolutely it is. There's no I behind it. It's not 0i. It's just 0. So you have one real root if the number underneath the radical is 0. If the number underneath the radical is positive, so let's say we were looking for the square root of 25. Okay, could we use bigger roots? Sure we could, but I'm trying to use smaller roots that maybe we're a little more familiar with. Okay, so the square root of 25, well, we know 5 times 5 is 25, but what a lot of people fail to remember is that, sorry, that's plus, negative 5 times negative 5 is also positive 25. Neither of those answers had i's behind them. They are real numbers. How many real numbers? Well, you have 2 real roots. 2 real roots if the number is positive. Let's jump over to the odd side. If the number underneath the radical is negative, so let's say we're looking for the cube root of negative 8. We're thinking what number times itself 3 times gives you negative 8. There's only one answer here, and that would be negative 2. That's a negative. Negative 2. Okay, that's not positive, that's negative 2. Bad handwriting. Okay, so the answer here, if the number underneath the radical is odd, or not, sorry, if this number is odd, then, and this number is negative, then our answer, there's only one real root. One real root. Nothing imaginary about that negative 2, it's just negative. Negative is fine. One real root. If the number underneath is 0, so let's say we're looking for the 7th root of 0. What number times itself 7 times gives you 0? Well, that answer has to be 0. I don't think there's, it's not that I don't think, I know that there's only one sign there. 0 is not positive or negative. It's just 0. So your answer here again, one real root. The last one, n is odd, a is positive. So let's go back to cube root, something that we can work with. Cube root of, let's say 27, positive 27. What we got to think is what number times itself 3 times gives you 27. Well, I know 3 works, positive 3. 3 times 3 is 9, times another 3 gives me 27. But if I use negative 3 times negative 3 is positive 9, times negative 3, got positive times negative, gives you a negative answer. And that's not positive 27. So, negative 3 is not an answer. When this number is positive and this number is odd, again, you only have one real root. Okay, so those are our 6 possible outcomes. Either no real roots, one real root, or 2 real roots. 2 real roots. It really depends on the number underneath and whether it's even or odd root. Okay, the next thing we did was some examples. Sorry about that. I'm going to switch pages here. So let's do some examples here. Find the indicated roots, indicated real roots. Find indicated real roots. We're really looking for the nth root of a. Okay, so number 1, let's say n is equal to, let's start with 4, and a is equal to, let's go with 81. N is equal to 4, a is equal to 81. So really what we're looking for is the 4th root of 81. Okay, remember the indicated real roots, we're looking for the real ones here. Depends on the what root we're looking for, whether it's even or odd, and then whether that number underneath is positive or negative. Obviously we can see that 4, the root we're looking for, is even, and 81 is positive. So if we go back to our table, let's bring that back. We had even and we had positive, which means we have two real roots. Okay, so now if you have that half sheet out, find 81 in the end of the fourth column. If you don't have it, pause it, get it out. If you look at 81 in the end of the fourth column and go all the way to the left, you find that the fourth root of 81 is 3. Well, that's one root. We need a second one. This is where plus or minus comes in. Positive 3 times positive 3 times positive 3 times positive 3 gives you 81. Negative 3 times negative 3 times negative 3 times negative 3 is also 81. We have two real roots, and they are positive and negative 3. Let's try another one. Number 2. How about n equals, let's go n equals 3, and a is equal to, let's see, how about negative 125? Negative 125. Okay, again, we're cube root of negative 125. Go back to your table. We're looking at the root that we're looking for, even or odd, the number underneath, positive, negative, or 0. When we've got cube root of negative 125, that would be an odd one. Sorry, that should be an underline. Odd one and negative. How many real roots? Well, we've got one real root. We need to go find it. Whoops. This button here, sorry, learning the new program. If you look at 125, find 125 in the end of the third column, go all the way to the left. You find that the cube root of 125 is 5, but this is not the answer because 5 times 5 times 5 is positive 125. I need negative 125. The way I get that is by making that 5 negative. So negative 5 is your only answer there. Let's try a couple more. Number 3. How about n equals 2, and we'll say that a is equal to negative 64. Okay, so if we make this, remember with square roots, if the number here is 2, you really don't need to write it. If it's not written, it is implied that it is a 2. So negative 64 underneath. Square root of negative 64. Well, with square roots under the radical, we know that's going to be plus or minus, since it's square roots, 2 answers. Square root of 64 is 8, but it's negative 64, so we need I. But we're looking for, again, real roots of a. We can't have this imaginary part. Okay? So the answer here is actually going to be no real roots. We cannot have that I. Okay? Last one, number 4. Let's see, how about n equals 5 and a equals, oh, what should we try? How about 1024? Okay, 1024. So let's write this with radicals. Fifth root of 1024. Find in the end of the fifth column, 1024 is there. Makes it work real nice. Go all the way over to the left and you find that the fifth root of 1024 is 4. The question then becomes, do I need plus or minus? Well, it all depends on this, the specific root you are looking for. Since it is odd, again, go one more time back to your table. When n is odd, the answer is always going to be one real root, one real root, one real root. So do I need plus or minus here? The answer is no. The only question is, does it need to be positive or negative? Well, if this number is positive, 5 negatives equals a negative. So I don't need the negative, I need the positive, because 5 positives does give me a positive answer. Let's move on now to rational exponents, because if we go back to the title of the section, way back up here, nth roots and rational exponents. We've talked about nth roots, that's done. Now we need to talk about rational exponents. Okay, so 1, 2, 3. Rational exponent. Rational exponent. Okay, rational exponents. Rational simply means, I'll put this off to the side and I'll write it in a different color. Rational means fraction. Sorry, ran out of room. That's fraction. Okay, anytime you see rational, it just means fraction. Okay, so the biggest takeaway from the notes the first time should have been this. If we have a to the m over n power. So now this numerator might be something other than 1. I'm going to erase this and rewrite it a little lower. So I've got a to the m over n power. This could go one of two ways. Go here or go here. Okay? And it's really just a matter of using exponent properties to decide which way you want to go. Okay, so I'm going to go with the top one as splitting it into the denominator 1 over n times the numerator m. That's an m. Let me try that again. M. Okay, or you can split it up where you go a to the m to the 1 over n power. Either one of those is absolutely correct. It's just going to be a matter of, do you want to find the nth root first, or do you want to raise it to the m power first? It's totally your choice. Most people, though, choose this method. It's easier to take something smaller and then make it a little bigger, rather than the method down here where you make something really big and then get smaller with the nth root. Okay, so to build off of this top one here, if we have the 1 over n power, remember we wrote this down earlier, right here, you circle it. If we have 1 over n power up here, okay, we can rewrite it using a radical with the denominator of your fraction becoming the root in your, or the number in the crook of your radical. So let me go back to the notes here. So we can rewrite this as the nth root of a to the m power. Okay, these two right here, these two are completely interchangeable. They mean the exact same thing. There's really no math happening from the one on the left to the one on the right. Okay, there's no math happening. It's just a notational change. They mean the exact same thing. Okay, similarly with the one on the bottom, we can make this the nth root of a to the m, where the m is now underneath the radical. Either one of those. Again, this is all notational change. They mean the exact same thing. There's no math happening in either of those two, going from step 1 that I'm going to underline here in yellow to step 2 that I'm underlining in blue. There's no math happening there at all. It's strictly notation. Okay, they mean the exact same thing. The other scenario we showed in class was if your exponent was negative, a to the negative m over n power. There's an exponent property that deals with negative exponents. We want to make negative exponents positive. We want to write them as positives if at all possible, and it is possible. We do that by making your base and exponent originally flip sides of what fraction they are in. If you don't see a fraction, obviously this is like over 1. So now this whole thing goes down to the numerator. The base and the exponent, the only thing that changes sign is the exponent. It's just positive m over n. If there's nothing left in the numerator originally here, then there's a 1 left. Let me write that a little better. It's a 1. If there was let's just say there was a 3 up here, then up here would remain a 3. But that's getting a little advanced or a little far ahead of ourselves. Really not what I'm after. Really what I'm after is understanding that with the negative exponent right here, we want to make it positive, and then once we get to this point, it's exactly the same as what's up here. Just it's now the denominator of your fraction rather than the numerator. Okay, so how we're going to use this is using it to, let me write an example here, evaluate the expression. Evaluate the expression. Pardon the handwriting, it's a little weird. So let's just jump into one. Number 1, 16 to the 3/2 power. Okay? Like I said, it's easier to make things smaller and then a little bigger rather than go really big and then come down. So what I see, for this one I'll write out both methods. Okay, so I'm going to kind of draw a couple arrows here. We can do this one of two ways. We can make this 16 to the 1/2 power cubed, or we could make this 16 cubed to the 1/2 power. Both of these are exactly the same. They will equal the same thing in the end. Mathematically, they are the same. Okay, with the one on the top, 16 to the 1/2 power is the same thing as the square root of 16 cubed. The square root of 16 is 4, and then 4 cubed is, if you look at your sheet, if you're not sure what 4 to the 3rd power is, go find 4 on the far left, go over to the end of the third, and that would be 64. This is your answer. Now, we should be able to get the same answer going the other direction. 16 to the 3rd power. Holy smokers, that's a big number. I put this in my calculator earlier. 16 to the 3rd power is 4096. 4096. And this is now to the 1/2 power. Remember, 1/2 power is the same thing as the square root, so square root of 4096. We don't have 4096 on our end of the second column, but if you do 4096 and square root it in your calculator, you do find that it is 64. Let's try another one here, number 2. We're going to go with 4 to the 5/2 power. These problems are exactly the same as what were originally given in the notes. So if you didn't get something written down, now's your chance. I will try to come up with a couple new ones here after this one. 4 to the 5/2 power. I'm going to do this one just one way. I'm going to take the, I guess you call it the top one, where we make it smaller and then make it a little bigger. Okay, so 4 to the 5/2 power. I'm going to rewrite this as 4 to the 1/2 power to the 5th power. I know that the 1/2 power is the same thing as the square root. Square root of 4 to the 5th. Square root of 4 is 2. So then 2 to the 5th. If you're not sure what 2 to the 5th is, it is on that half sheet table. It is 32. All right, let's try another one. Number 3. This is a new one. We're going to go with 256 to the -3/4 power. Okay, this one's new. 256 to the -3/4 power. What I see first is the negative exponent. I want to take care of that right away. So 256 to the +3/4 in the opposite side of the fraction, in this case the numerator. There wasn't anything left up top, so it's going to be a 1. Okay, now we're just going to focus on the bottom, because the top is not going to change. It's always going to be 1 over something. Okay, so 256 to the 3/4 power. I'm going to rewrite that. I'm going to skip this step up here in the last problem where I wrote it as a fraction and then convert it. I'm going to go straight to the radical notation. The bottom number here is your number in the crux, so that's going to be a 4, 256 underneath, and then cubed out front or out behind it. 4th root of 256. 256 is in the end of the 4th column, so the 4th root of 256 is 4. So 1 over 4 to the 3rd, and then lastly 4 to the 3rd. That is 64. So our answer then 1 over 64. Hopefully that makes sense to you. If not, there are a couple more examples in the book. There are also some videos in the online textbook that might be able to explain it in a little different way that hopefully makes sense to you. The last thing in the section was solving equations using bigger roots. Okay, so example here, we're going to solve. Number 1, this one was in the notes earlier. 4x to the 5th equals 128. Now, in chapter 3, when we were solving with square roots, if we had something like 4x squared equals, let's just say it was 36. Okay, our steps would be to get x squared by itself. So we're going to do that by dividing by 4. X squared equals 36 divided by 4 is 9. And then we need to square root it. The reason we square root because we want to undo the square. So x would be equal to 3, but 3 wasn't right. Remember, even root, positive number, 2 answers, plus or minus. We're going to do the exact same thing with bigger roots, but instead of using square roots, now in this case, we're going to need a 5th root. But we're going to need to do that here not quite yet. We need to get rid of this 4 first by dividing. We want to get the base of x all by itself. Okay, so the 4's are going to cancel away. We're left with x to the 5th on the left. 128 divided by 4 is 32. That's a really nice number because our next step is to take the 5th root of both sides. Okay, the 5th root and the 5th power cancel each other out. We're left with x on the left-hand side. Fifth root of 32 is a nice number. It is 2. The question then becomes, is it positive and negative 2, or is it just positive 2? Go back to your table if you're not sure. This one way here. Fifth root makes it an odd root. Positive 32, that's here. One real root. So I do not need plus or minus 2. It is just 2. There's only one answer. Let's try another one here. Number 2. Let's go with x plus 5 in parentheses to the fourth power is equal to 16. Now this one's a little different because the x isn't part of, it's not just its singular base. So let's think about this backwards. Let's say that I told you that x was equal to 7. I'm just picking a number. And I wanted you to tell me what that whole thing is equal to when it's equal to 7. If we plugged in a 7 here, our first step using the order of operations would be to add 5. After we add 5, then we do the exponent. Okay, so we'd have a two-step equation or a two-step evaluation. But let's bring back the original problem. The answer here was 16. When we want to solve this, we need to undo this list over here in the opposite or in the reverse order. So the last thing we did was the exponent. That's the first thing we need to get rid of. The exponent here is 4, so we're going to undo it with a root, specifically the fourth root. The fourth root and the fourth power cancel each other out. Okay, so the fourth root, fourth power go away. Left side is left with x plus 5. Now, 16. If you look in the end of the fourth column on your half sheet, 16 is there. If you go all the way over to the left, the fourth root of 16 is 2. But it's not just 2. It's an even root, and it's a positive number, which means you have two answers, positive and negative 2, plus or minus. Okay? So adding or getting rid of the exponent is done. Now we need to jump to step 2, which is adding 5. The opposite of addition is subtraction. So we subtract 5. I'm going to slide this up just a little bit, maybe. There it goes. Okay? If you just put x equals plus or minus 2 minus 5, negative 3, that is incorrect. Okay, that's not how this works. Okay, so let's start this again. Really, we need to think about this in two ways. We need to think about this as 2 minus 5 and negative 2 minus 5. These are nice numbers. We can keep going with these, or we can work with these that, this isn't that difficult of an answer. We do have two answers. 2 minus 5 is negative 3, and then negative 2 minus 5. If I owe $2, I borrow 5 more. That means I am down, not 5, sorry, 7. Okay, so we have two answers, negative 3 and negative 7. Let's try just one more. Okay, we're almost done. The video's almost over. Number 3. This one is x minus 2 to the third power is equal to negative 14. Okay, very similar to this one here, where we have the x is not its standalone base, so we need to kind of work our way from the outside and in. The steps, if we were to erase the negative 14 and evaluate at a specific x value, would be the same. So I'm not going to go through the list. The first step here is the cube root of both sides. The cube root, cube, cancel. We're left with x minus 2 on the left. That's a cube root, sorry. The cube root of negative 14. Negative 14 is not a nice number as far as cubes are concerned. I do want to leave this as an exact answer, though. So I'm just going to leave it as the cube root of negative 14. That's all I can do with it. Okay? One last step. Add 2. Add 2. So x is equal to, I can't combine these two. Doesn't go into that. So I just leave it as either one of two ways. You can go 2 plus the cube root of negative 14, or the cube root of negative 14 plus 2. Just make sure that this plus 2, it's very clear that it is not inside the radical. To do that, like I just did there, put a little tail on the end of it and close off the bracket. Hopefully that helps. Let me know if you need more help.